Our next speaker is Cait Martinez, who's a PhD student in atmospheric sciences, and she's going to talk about things related to ENSO predictability. Go for it.
Thank you. Hi, I'm Cait. Today I'm just going to kind of show some new results that I have in my attempt to build this advanced framework for disentangling deterministic dynamics from stochastic processes. So the El Niño Southern Oscillation is the dominant mode of climate variability in the tropical Pacific, and it plays an essential role in modulating the global climate through its teleconnections. And as a coupled phenomenon, ENSO is inherently multivariate, and coupled feedbacks are central to generating ENSO events. However, debate persists on which initiation mechanism dominates, and consequently there remains a lack of consensus in its predictability. And so I posit that a key challenge in predicting ENSO lies in its sensitivity to stochastic processes. So ENSO is driven by interactions between the atmosphere and the ocean, and these interactions involve an exchange of energy and momentum and are critical for creating and amplifying ENSO events. And one of the key processes is the Bjerknes feedback. In a nutshell, anomalous SST drives changes in atmospheric winds, which in turn enhance the SST anomalies through this air-sea coupling. And this coupling introduces this direct relationship between surface wind stress anomalies and the state of the Niño 3-4 SST. But ENSO isn't just about surface processes. Subsurface preconditioning plays a big role. And subsurface preconditioning refers to the buildup of subsurface heat anomalies, or these large reservoirs of warm and cool water below the ocean's surface. And they often emerge months before an El Niño or a La Niña. And these subsurface precursors are considered the main source of ENSO predictability. However, the role of atmospheric noise remains unclear. And what I mean by atmospheric noise is these random, short-lived atmospheric fluctuations that can perturb the system. And because not all variability is associated with ENSO can be explained by these deterministic processes like the precursor, we must account for these stochastic processes in our estimates. So my research is really interested in this question: how much of ENSO is driven by deterministic dynamics versus stochastic processes? And then what are the implications of that on ENSO predictability? So for simplicity, we can define deterministic dynamics as subsurface preconditioning, sometimes called the subsurface precursor, and stochastic processes as the atmospheric noise. And to really even begin answering this question, we have to first separate these two categories of processes. And there are a few methods to do this. One approach is to remove the subsurface preconditioning to see if ENSO even still develops. Previous studies show that suppressing ENSO variability can provide a baseline for understanding the climate system without the influence of ENSO. So these figures here show results from two of my predictability ensembles, each consisting of 60 one-year forecasts. And I ran these in the CESM2 coupled general circulation model. And the only difference between the two is that the two ensembles is the initialization month. So each ensemble is initialized from an ENSO-neutral simulation, where the ocean's wind-driven dynamics is decoupled from the atmosphere, effectively severing that Bjerknes feedback. And when the decoupling restraints are lifted in month 0, the system is allowed to freely evolve. So the red and blue lines indicate El Niño and La Niña events, defined here as the Niño 3-4 SSTA that's exceeding plus or minus 0.5 degrees Celsius in December. And clearly, we can see that a lot of ENSO-like events can be initiated and grow to substantial amplitude without ENSO cycle preconditioning. But even when we restrict the thresholds to even restrict the thresholds more, we see that extreme El Niño events occur 11% of the time when the forecast is initialized in March. And so one interpretation of this result is that by reinstating dynamic coupling from that ENSO-neutral initial condition documents the unpredictable component of ENSO. And these results agree with previous studies, and they suggest that predictability may not entirely hinge on subsurface preconditioning, and thus underscoring this importance of including these noise-driven processes in the predictability estimates. Okay, so how do we separate the noise from the signal? Well, the simplest approach is this regression-based decomposition framework of the ENSO-related signal and the noise. And so the anomalous wind stress is a function of latitude, longitude, and time, can be expressed as the sum of the ENSO-related signal and the non-related noise. And then building on that relationship between wind stress and SST, the December Niño 3-4 SSTA is then modeled as a linear function of the zonal and meridional wind stress anomalies. And if we define the ENSO-related signal as the anomalous wind stress, as the component of the wind stress that can be reconstructed, using the regression coefficients and then scaled by the Niño 3-4 SSTA. Then the noise then represents the residual portion of the anomalous wind stress that's not explained by the ENSO-related signal. And then we can visualize the patterns and look for spatial structures. So this figure shows the spatial structure of the ensemble mean at signal and noise patterns in that anomalous zonal wind stress for the March release experiment over the tropical Pacific region. And the signal's in the top row and the noise is in the bottom row. And for the months of March, September, and December. And as expected, nothing really stands out in particular. But when we isolate just to those 3 ensemble members where extreme El Nino events develop, we no longer see that white noise pattern in the noise, and we can start to see some spatial structure developing in March, September, and December, and possibly even persisting throughout the year. So just a few kind of like main takeaways from this beginnings of this work here is that we know coupled feedbacks are critically important in the tropical Pacific, but the role of atmospheric noise in shaping ENSO growth remains unclear. The CESM2 release experiments from the ENSO-neutral initial conditions show ENSO-like growth in both March and September initializations, and a simple regression-based signal and noise decomposition exhibits some spatial structure in the noise in the March preceding an extreme El Nino event. Now, to add sophistication to this simple linear signal and noise decomposition, I plan to take my research in 2 additional directions. So 1, I plan to implement the interactive ensemble coupling approach to minimize the atmospheric noise that's felt by the ocean at the air-sea interface. And this IE method just can provide a mechanistic diagnosis of the coupled feedbacks and the uncoupled atmospheric noise. And 2, as an iDisk fellow for this academic year, I'm working on integrating machine learning methods to explore the relative importance of the subsurface preconditioning and the atmospheric noise contemporaneously. And so my goal here really is not to build a prediction system, but instead to enhance our understanding of the dynamic drivers of ENSO variability without just removing the noise or without just removing the subsurface preconditioning. Thank you.